Hello student, hope so all of you are fine and you are watching this video. This is sound waves part number 1, which one we are going to learn for today. Uh, Already we discussed some of these parts in last class regarding loudness, pitch and the 3 questions and answers. So today's lesson objective to learn about the basic principle of sound. Now see over here that how we can segregate the different parts of the waves. Already we learned about the water waves. We are learning now sound waves. We have finished light wave, reflection of light, light refraction, light dispersion, and lenses. So these all parts already we have finished. Today we are going to learn about sound waves. Now lesson objective for today. First, number 1, properties of sound waves. Number 2, behavior of sound waves. Number 3, loudness and pitch. And number 4, that is a bit interesting, measuring speed of sound. So these are the 4 different parts. So for first one, let's go to begin. Properties of sound waves. So over here in this segment, we are going to learn many different behaviors for sound waves. So the sound waves, you can see over here that direction of vibration and direction of wave, how both of these two, they will change together. First one, sound is produced by vibrating objects. You need something like guitar. You can see the string of the guitar. If you like to press it, or even you can see over here that the tuning fork, that is also we can use a pith ball, and if we like to hit by using a pith ball, P-I-T-H, pith ball. And this machine that is called tuning fork, T-U-N-I-N-G, tuning fork, F-O-R-K. Okay, so this is called tuning fork, and we need a pith ball. And if you like to hit this tuning fork by using the pith ball, then you can find that the process, or you can find, or you can create the sound. And over here you can see that the vocal cord, that breathing open passages and taking closed passages. So whenever that is closed passages, that means we are trying to talk, and whenever the passage that is opened, that means we are taking our breath. That means either we are taking or we are just getting it out. So these are the sound is produced by vibrating objects. So if you like to produce a sound, then you must need an object which one can vibrate the air molecules. You can see over here one is string, and this is our ears. So if you like to pull the string left to right, then you can see that both of these, the string, it can create some vibration inside these air molecules, and you can see the compression part, and as well as you can see the rarefaction parts. Rarefaction parts, the pressure that is less, air pressure less, and for compression part, air pressure that is more, high dense air molecules. So over here you can see that the direction of vibration and direction of propagation, both of these two are parallel. Let me explain you again that how it works. You can see that whenever this is string, we are just vibrating or pulling in this side, left side, and we're just releasing it. Then the string, it starts to vibrate left to right like this. So direction of vibration left to right. That means direction of vibration for air molecules, air particles, they are also moving left to right like this way. Now the Direction of wave, sound wave. Sound is also traveling from this string towards this ear. That means direction of wave from right to left, and direction of vibration left to right, right to left, like this. So both of these two directions, see, can you see this red line and the direction of this particle? So both of these two are parallel. All right, direction of particles are also moving left to right, and direction of wave is also going on from right to left. So these two lines are parallel. That's why this is called longitudinal wave. And already we learned in last class that we are having three very tiny bones inside our ear, and whenever these air molecules, they will come and they will hit towards the external part of our ear, then what will be happened? These vibration of air molecules or disturbance of air molecules, they will come and they will hit this part of our ear, external part of our ear, and this one will go or transmit through this channel. This channel over here, we're having three bones, and they will change it from this signal, external signal, to internal signal. And this whole transmission of energy, it will go through a channel that is called cochlea, and this cochlea, that is completely filled by liquids. That means over here the sound that is on air, then after that these three bones, they are changing the sound waves to the another signal, and those signals are transmitting, or that energy is transmitting through this liquid channel, and from here it will again create some another type of vibration over here. And over here we are having some elastic tissue, cochlear tissue. We are telling that cochlear tissue. So those cochlear tissue will also, it will vibrate, but that is very less, so that we do not understand nothing about that. And it will create different frequencies of sound, but that is very low frequency signals. So these signals, it will go towards your brain, and brain will detect, oh, this is Mr. Shahid and he is teaching you sound. It makes sense? Ah, right. So it does make sense, right? That means brain can detect different voice. If you can hear my voice, you can detect that this is Mr. Shahid. If you can hear Mr. Hassan Sahab's voice, he is your chemistry teacher, you can identify, oh, this is Mr. Hassan, the chemistry teacher, this is Mr. Shahid, physics teacher, or even the English teacher, or even the other teachers. That means the brain, the neuron, they will save those different voices, that means the different tones. That means this part, this cochlear tissue, it will create different tones for the different people, and it will transmit those signals towards our neuron, and neuron will save it inside their database. Okay, the neuron, the brain, it will save those sounds, and whenever this person again, he or she will speak out, then a neuron will match from its previous data about the sound, that which this sound is matching with which person or which type of sound. Then the neuron will tell you that, okay, this is Mr. Shahid, that is a bird, or that is a cow, that is a dog, or even that is an animal, or that is a whistle, or that is a sound from a car. That means these all different sounds, brain, our brain, so brain is saving these all signals. So this cochlear and this cochlear tissues, so they are actually helping to create these different types of sounds, and they're sending it as a signal inside our brain, and brain is saving those signals inside our brain to detect it in future. So hope you understand the process for how sound is produced by vibrating objects. Right, that's great. Now move on to the next segments. Sound waves are mechanical waves. We learned last day that there are two different types of waves. One is that mechanical waves, another one is electromagnetic waves. And we also learned that for mechanical waves, we need a medium. Without medium, mechanical waves can't travel. But for electromagnetic waves, no need for any types of medium. So electromagnetic waves, it can travel from one place to another without any medium, right? So over here we are going to learn about an experiment that sound waves are mechanical waves. So how we can identify or how we can understand that sound waves are mechanical waves. You can see over here a vacuum pump, and inside the vacuum pump you can see a bell, and there is a cork. You can see here there is a cork and a bell, and over here electromagnets, right? And it will also, so a mechanical wave needs medium to travel. If we pump out air from the vacuum jar, the sound of the ringing electric bell becomes quieter. You can see over here a pump, and we can take out this air, the trapped air, from this jar slowly. So at the beginning you can hear the sound, and whenever very slowly we are just taking out the water through this channel, then you find that the sound wave, it will decrease. After a certain time you will see that you will see the vibration of this bell, but you can't hear any sound. So if air is completely removed, even the bell is still working, no sound is heard. That means we understand from here that sound needs medium to travel, and the medium over here, that is right, that is air. All right. So this is also, if I like to ask you the question that proof or write an experiment to find out that sound is a mechanical wave. So you need to write that answer. Over here you can see an astronaut, that an astronaut needs communication devices because they cannot hear each other in space, because sound does not travel in space. We know that, right? The sound can't travel in space because on space, no air, no medium. Now again to the next part, this diagram, please do draw it to your notebook. The sound waves are longitudinal waves. You can see compression, rarefaction, again compression and rarefaction. So the longitudinal wave is a series of compressions and rarefactions where air molecules vibrate parallel to the direction of the wave propagation. Wave propagation means wave direction. Look, you need to understand two directions. One is wave direction, one is molecules vibrational direction, or from which side the molecules they will vibrate. Okay, so you need to be very careful about these two directions. One is that the wave, main person, who is going on from which side. So the main person, main culprit, the wave, say like the wave is traveling from left to right, this side wave is traveling. Now the second question, direction of vibration for the air particles, air molecules. So direction of vibration for the air particles also going on left to right, like this. So these particles are moving left to right, and the result of this vibration, the main wave will also travel from left to right. So whenever these two are parallel, that is called longitudinal wave. And like that, these waves are traveling up and down. So vibrations are going on up and down, but the wave is traveling left to right. So that is perpendicular direction. Then we will tell that that is a transverse wave. So please learn about compression in sound wave. It is the region where air molecules are close to each other, the high pressure region, right? And the another one is the low pressure region. So rarefaction, it is the region where air molecules are far apart from each other. So please write it to your notebook and memorize it. Now see this diagram. Do not be confused that this is the diagram for transverse wave. Actually, in this diagram, we are trying to show you the air pressure versus time graph, distance graph. See over here. Do not think that this graph, that means this is transverse wave. Look, this graph that is representing air pressure versus distance, and the transverse wave, it will show you distance versus time. Okay, the distance or displacement will be in this side, and in this side it will be time. Then it can be the transverse wave. But this graph, y-axis is air pressure and x-axis is distance. That means this is not transverse wave. Over here you can see that air pressure is 0, and then air pressure is slowly increasing to the opposite direction. Then air pressure is again coming, and over here air pressure is 0. Okay, then again air pressure is increasing, and over here maximum, like this. So do not be misguided to see, or do not think that this wave means transverse wave. You need to see that what is written here and here. All right, now see here for the rarefaction, the molecules are a bit different types. You can see here that rarefaction, a high pressure region and low pressure region. So these are the low pressure region, which one we are talking about, and the other side, that is the high pressure region. So the low pressure region is the downside, the negative parts, and the high pressure region is the positive parts. That means the crest and trough. That means see over here that the crest parts, these are the crest, right? Crest. So the crest part will tell that these are the high pressure region, and this is low pressure region. Over here, look, the gap is larger, means pressure very less. People are farther apart. Like now, all of you are in, say, like 35 students in your class. Now you will be 35 for the next 3 years almost. That means you are having a very good combination. You will find very good friends, even some enemies, right? But after 3 years, maybe some will go to Canada, some will go to Australia or USA or UK or different sites. Then after 10 years, means today 2020, so 2030, you will find that your school classmates, they had gone in different directions. So you will find that you may just, there will be very less connection in between, so very less pressure, like here. So far apart means very less pressure, and over here close together means high pressure, relation very good. All right, so please do not be misjudged with this graph. This is not a transverse wave. This graph is air pressure against distance. All right, so transverse wave will be that distance versus time, or displacement versus time, then that is transverse. Now see the another experiment. Sound waves are longitudinal waves. How can we even determine that sound wave is a longitudinal wave? Before that we learned sound wave is a mechanical wave. I showed you the experiment. Now this is the another experiment where we can determine that sound waves are longitudinal waves. See over here the pith ball, sorry, this tuning fork. If you like to hit with a pith ball to this tuning fork, then the tuning fork, it will just move left to right, and whenever the tuning fork, it will just move left to right, then you can see that the wave that is going on from right side to the left side. So this is the direction of the wave, and these are the what direction of vibration for the particles. So both of these two are parallel, so this is a longitudinal wave. I think it's very easy. It seems to be very easy for you to understand it. So please draw this diagram, and as well as some description, whatever I say to you, or in your own language, that how can you prove that sound wave is a longitudinal wave, and also how can you prove that sound wave is a mechanical wave. Now the next segment, sound travels faster in solids than in liquids than in gas. You can see the solid molecules, they're very close together. You can see at the middle, this is the liquid one. Over here the molecules are a bit farther away, and for the gas the molecules are very farther apart. Now see that for speed in air 330, speed in water 1400, speed in concrete 5000, speed in steel 6000. So you can see over here the different parts, that how these four parts or four different categories are changing. Now sound speed increases as temperature increases. Correct, right. So as the temperature will be high, that means there will be low air pressure. That means the sound can travel more faster, and it can travel even longer distance. Sounds with frequencies between 20 Hz and 20,000 Hz are heard, and this range is named as audible range. Hope so already you came to know this segments in the previous class, even in your middle school. So less than 20 Hz and more than 20,000 Hz, right? So you can see here less than 20 Hz, that is called sub sound, or even sometimes the different name, infrasonic sound or sub sound, SUB, sub sound. And this side more than 20,000 Hz, that is ultrasonic sound. So we cannot hear infrasonic and ultrasonic sound, but we can hear only audible sound. Alright, so this is very easy, but you need to remember it. This is very important for MCQ, multiple choice questions. Right, move on to the next part, properties of sound. Sound is produced by vibrating objects. Sound waves are mechanical waves. Sound waves are longitudinal waves. We have done 2 experiments. Sound travels faster in solids than in liquid and gas. Sound speed increases as temperature increases. And sounds with frequencies between 20 Hz and 20,000 Hz are heard, and this range is named as audible range. So hope so you understand this video. This is sound waves part number 1. See you to the next video. Thank you. Bye bye.